Okay, we are in 19.6 magnetic torque. This is also going to include 19.61 on electric motors. Um, so let's start with sharing the uh, PowerPoint. And here we see a loop, magnetic forces acting on sides with current perpendicular to B, but not on sides with current parallel to be. So if you look at the figure, the you'll see there's an A. The width is a small a, and the length is B. So those currents that are along B that are parallel to B, there's a force on them. Those in parallel to A, there is no force because uh, the the sign of theta there is, I mean, theta in that case is 0 or 180, so there is no force on them. But if you look at, now we're looking at a cross section, or they're taking that loop and they're turning it on its side, and we're looking at the if you want a bird's eye view, the forces F1 and F2 on the sides of length B create a torque that tends to twist the loop clockwise. So we've got the magnetic field, we've got the um, on the left uh, on the left side of that second image B, you can see that the current is coming out of the page. So you've got the magnetic field, the uh, current coming out of the page, and the force up. Now let's go to the other one. The magnetic field, the uh, current going into the page, so the force is down. So you can see there's a two-way torque. I mean, uh, a force upward and a force downward. Well, the force is equal to you remember it's BIL. Well, what is L? L is the lowercase b. So F1 and F2 are both BIB, where the B is of the length of uh, the conductor. Uh, Now let's look. Now torque, if you recall, torque is equal to a force times a lever arm, a moment arm. And what is the moment arm? Well, it's right down the center, so that's A over 2. So you've got one force, force 1 times A over 2 plus force 2, A over 2. Well, that's the torque. So it's BIB A2 plus BIB A over 2. So it's just BI AB, lowercase b. Well, what is AB? That's the area. So the torque is equal to the magnetic field B times the current I times the area of the loop uh, that you have here. So it's the area of this square loop. Um, Now, let's look at the moment arm. The moment arm is A over 2 sine theta. Um, and what the moment arm is, it's a vector that is perpendicular. So here you can see that this plane of this loop, the um, the the moment arm. Oh, I'm sorry. Uh, I jumped the gun. It's not magnetic moment. It's the the moment arm is A2 sine theta. Of it's the projection of A2 um, onto the perpendicular of the force. So the moment arm here is A over 2 sine theta. If B is at an angle theta with a line perpendicular to the plane of the loop, the magnitude of the torque is given by BIA sine theta. If you recall that we had BIL sine theta when the magnetic field is not perpendicular to the wire. It's a similar case here. So torque is equal to BIA sine theta. Uh, BIA times the number of turns sine theta. This is just for a single loop. If you have a number of turns, that's sine theta. And we're going to call mu the magnetic moment of the loop, and it's IAN. The mu is IAN, so the torque is equal to mu b sine theta. Well, what is mu? Mu is the vector that is perpendicular to the plane of the loop, and you can tell whether, in this case, you have two options. You can have a vector going up, or you can have a vector going down. But the way to determine it is it's perpendicular to the loop, and your fingers curl in the direction of the current. So in this case, it's coming out of the page. So my fingertips are the points that kind of like lavender or pink dot. It's also the pink X's. So in one case, my fingers are coming out, and there's the moment arm. In the other case, the fingers are going in, and there's I said moment arm. It's magnetic moment. So the magnetic moment is perpendicular to the plane, and it's determined by the current. Your fingers wrap in the direction of the current. If we reverse the current, then the magnetic moment would be this direction, and it would point down. So torque is equal to mu b sine theta, where mu is Ia, the current times the area times the number of turns. Okay, if B is at an angle theta with a line perpendicular to the plane of the loop, the magnitude of the torque is given by BIA sine theta. Now, let's look at motors, and you can see there's a magnetic field. There's a magnetic field there. There's a current this way, so the force is going to be turning this in this direction. Let's go to our old friend Walter Fent, and he's got a let's start here, and you can see now this is a split ring motor, and that, in other words, it reverses. It keeps the current going in the same direction. The momentum of the little motor will keep it going past the little split ring, so that it continues. Just for that momentary switch of the current in the loop, where you get a pause, but the momentum will take it. And you can see, let's just pause it. You can see there's a magnetic field, there's a magnetic field, a current, and the force on the top, a magnetic field, a current, and a force on the bottom. And you can see that it just continues to drive the motor. So we can change the direction. How do we change the direction? By changing the polarity of the battery. If you look now, the plus is on the bottom and the minus is on the top. Let's change direction again. See the plus and the minus change. Okay, well, I think that's enough of Walter Fent. Thank you, Walter Fent. Let's pause it and go back to the PowerPoint. All right, let's. And here's an electric motor. This is an electric motor from a Toyota hybrid. The engine compartment of the Toyota Prius, a hybrid vehicle. The figure shows a modern motor used to power a hybrid gas electric car. All right, I think that's it for the electric motor.